In this video, we're going to look at Cox proportional hazards. It's a survival analysis. The outcome variable is time to a discrete event. We're going to use the Worcester heart attack data. There's an ID, the date they were admitted into the hospital, and the date they ended up their last follow-up date. It gives the length of time they stayed in the hospital. This could be as probably in hours. Follow-up status, 1 means they died, 0 means that they either, they were still alive when the study terminated. There's the age of our people. Gender, male and female, and body mass index. So when we analyze, it's going to be a regression equation. So it's the follow-up time, and we look at time until death. That's the kind of those two make up the y equals length of stay, age, gender, BMI. Those are continuous variables in a regression equation. So we're going to analyze survival. We've done the Kaplan-Meier curve. Now we're going to do Cox regression. Cox time-dependent covariate. Let's say in the Kaplan-Meier we had surfactant. Well, if at different points in time they had changed the dose of surfactant, you might want to keep track of time under given doses. So that's a pretty complicated, can be a complicated type of variable. But we're just going to do the straight Cox regression. We have follow-up time. We have status. Now, we need to define when the event occurs and what's the value of it. And it's going to be a single value, and it's a 1. Then we have our independent variables, hospital length of stay, age, gender, body mass index. And we could do a stepwise and bring them in one at a time. The only problem with that is you could find some variables that if you controlled for other variables that would come in. The other bad part about it is if there's a lot of multicollinearity, it would cancel out different things. So it's not a bad idea to do it both ways. We're going to just do it as entering into it. Categorical, the only categorical data we have is gender, which we could go in and define here, but gender is already defined with just 0 and 1. You don't, when there's just two variables labeled 0 and 1, there's really no need to do a categorical variable. The plots, we want a survival. That's starting out, everybody is alive, and then the graph goes down as people die off. The hazard ratio, maybe we'll take a look at that. And options, we have confidence interval, nothing really to change here. So here it is. There are, out of the 100 patients, there were 51 deaths. So 49 were still alive at the end of the study. There were no cases with missing values. That's pretty good. No cases with negative time. That's good too. It's good that you don't die before you were admitted to the hospital. It's pretty bad when you admit a dead guy. Censored cases, there were none before the earliest event. You don't really want to have a case where your study ends before the first event happens. So that usually requires some extra work to evaluate. Here we have the overall chi-square is significant. Now, I will have to say that, well, yeah, this is a measure of model fit. And a significant chi-square means that the model didn't fit very well. but you almost always have a rejection in a model when it's not based on the null hypothesis. It's based on the model that you've set up. That almost always is significant. Our variables in the equation, we can look down here and we see that there is age and BMI. We have our regression weights over here. If we wanted to rank order on importance, we would see that the Wald statistic is greatest for age and next greatest for BMI. The hospital length of stay and gender are actually not too significant. You would say, well, I would think gender would be, but remember, these are all patients who started out in the study by having a heart attack. So you've already taken the advantage of being a woman away by having that, by the sample. Now, these these components, what do they mean? What these refer to is, and the hazard, this is the, it's proportional hazards. Proportional hazards are the same thing as relative risk. It's just another way of saying relative risk. It's not exactly computed the same because these are continuous variables, but the concept is the same. And age, now you'll notice, well, where 1 is no difference. 1.039, that's the close to the smallest value of increase over 1, but the most significant, the most important, and that's because age, for every year you get older, you increase your risk of dying by almost 4%. So we can see that we're not, well, for one thing, we're not accounting for a lot of variance in this variable, but there's a lot of variable. If you remember from the data, there were people that were, in their 40s to 80s. So it's a wide range. And so each little piece, if we calculated the standard deviation for age, then we could determine what percentage of increase in death would be for a 1 standard deviation increase. This is just 1 unit increase in the proportional hazard. That looks like that's good. Here's a survival function. Starts out at 1. People are dying at almost pretty... So you can see right after they're discharged, a lot of people will die. But then it kind of goes into a linear sort of thing, and then it's kind of crashing near the end after this long period of time. It was a pretty long follow-up. Just, again, sort of a similar kind of thing going in an increase. That doesn't really tell us too much more. The hazard increases as you get older, just as 1 minus their survival curve. It's not exactly the same curve, but it's similar. Okay. I think that might be it. Yeah. All right.